Hello everyone. In the previous video, we have proved that the vertical projection of a uniform circular motion is simple harmonic, and we have also derived an expression for the displacement of the particle in simple harmonic motion as y equal to a sine omega t, where y is the displacement, a is the amplitude of the oscillatory motion. We'll begin our discussion right from there. Once you got displacement for the particle in simple harmonic motion, to get the velocity, we know velocity is rate of change of displacement. I just need to differentiate that equation d by dt of displacement. Displacement we have found it as a sine omega t. A is a constant that can be written out of the differentiation and sine of omega t. We know differentiation of sine theta is cos theta. So differentiation of sine omega t is cos omega t. We are differentiating with respect to t, but there's an additional factor omega. So as per the chain rule of differentiation, here I will get one more omega. That's the chain rule of differentiation. You shall know that. So velocity of the particle is a omega cos omega t in simple harmonic motion. Sometimes this can be used as an expression itself for the velocity. But we can extend further and get some more derivation, right? From here you can write y, get this a to the other side, y by a is equal to sine omega t. Once if you know, say sine omega t, you know another formula that there is, yeah, we know there is a formula that sine square theta, here theta is omega t in our case, and cos square theta is equal to 1. From that, I can write cos square omega t as 1 minus sine square omega t. From that, I can write cos omega t as taking a square root on both sides, 1 minus sine square omega t. So from here, I can write sine square omega t as y square by a square, and I can substitute this value here. That implies I will get cos omega t as square root of 1 minus sine square omega t means I can write y square minus a square. So in the place of this cos omega t, I can simply substitute this value so that I can get another format for the velocity of a body in simple harmonic motion. So let us do that. Velocity is a omega. In the place of cos omega t, I can write whatever I have derived just now. Root of 1 minus y square by a square. So that is a omega root of a square will be the LCM, a square minus y square. So if I simplify this further, a omega root of a square minus y square. By square root of a square is a itself. This a and a can be cancelled. Thus I get an equation for velocity as omega root of a square minus y square. This is another format of velocity. So you can notice there are two formats of velocity, two equations for velocity, either a omega cos omega t or omega of a square minus y square. We can use any of this equation, any one of this equation, depending on our requirement. Now, from here, I can further write few things like, yeah, what we can write. If y is 0, v becomes omega root of a square minus 0 square, that is omega a. That's the maximum possible velocity. If y is a, that means 0 means you are at a mean position. So at mean position, you get maximum velocity for a particle in simple harmonic motion. Y is a means it is at an extreme or interim position. In that case, velocity becomes omega root of a square minus y is also a square. So velocity becomes 0. So you can have velocity 0 at a main position, at an extreme position. And at main position, velocity is uh, maximum. So what do you mean by that? What is the take away from that, if you try to understand little carefully, this is the main position. Say, for example, this is one extreme position. This is another extreme or interim position. At mean position, so if the particle is moving like this, velocity is maximum. So it always drives towards the interim position. Here velocity is zero, then it returns back, right? So when it comes here, again it is maximum. So it will be driven towards the extreme position. At extreme position, again velocity is zero, then it goes back. Thus the oscillatory motion to and fro continues because of this kind of characteristic called something like a oscillatory motion. Now, as you got an equation for velocity, now I want to do further expression for acceleration of the particle, right? Let's do that. Acceleration. So velocity is over. I want to derive an expression for acceleration of a particle. Velocity equation we have derived just now as a omega cos omega t. We want to find out expression for acceleration. We know acceleration is rate of change of velocity. That's a definition of acceleration. That is d by dt of a omega cos omega t. A omega is constant that can be written outside the differentiation. You are differentiating with respect to time and cos omega t. Differentiation of cos theta is minus sin theta. But be careful, you are differentiating with respect to t, but you have an extra factor omega. So as per the chain rule, as I said earlier, I'll get another omega factor. That's called chain rule of differentiation. So this big equation is minus a omega square sine omega t is the equation for acceleration. We can use this as one equation. But if you notice little carefully, earlier I have written, yeah, displacement is, we have derived an equation y by a equal to sine omega t. That implies sine omega t is y equal to a sine omega t. That implies sine omega t equal to y by a. I can just substitute that value here. Yeah, minus a omega square. Differentiation sine omega t is equal to y by a. This a and a will be cancelled. So acceleration is equal to minus omega square y. That's an expression for the acceleration of a body in simple harmonic motion, where omega is angular velocity. As the body is in uniform circular motion, angular velocity is constant. As omega square is constant, acceleration is directly proportional to minus y. So here it says two things. What is that two things is? Acceleration directly proportional to displacement, and the negative sign indicates that they are in opposite direction. Hence, we have satisfied three conditions now. First thing, we have already proved it as a to and fro motion, vertical projection of a uniform circular motion. Second, we have proved acceleration is directly proportional to displacement. Third, we have proved that there is a negative sign indicates that it is in opposite direction. As all three conditions are satisfied, vertical projection of a uniform circular motion can be explained, can be proved as a simple harmonic motion. That's what's the meaning of a simple harmonic motion. Acceleration shall be directly proportional to displacement, and both of them shall be in opposite direction. As you got a equal to minus omega square y, we can write at mean position displacement is zero and hence acceleration is zero. At an extreme or interim position, displacement is amplitude and acceleration is minus omega square a maximum. So, if you notice little carefully what we have found in, say here, at the mean position, we found velocity is maximum. Yeah. But at the mean position, acceleration is zero. So here at this position, mean position, velocity is maximum, but acceleration is zero. At extreme position, velocity is zero, but acceleration is maximum. So these are in opposite direction, and one increases, other decreases, and they work in opposite direction. That kind of a motion is called as a oscillatory motion. And finally, quickly, I want to derive one small equation. As I proved, acceleration is equal to minus omega square. Why minus is symbolic? It is in opposite direction. Magnitude of omega square is a by y. Omega is square root of acceleration by displacement. Omega is rate of change of displacement d theta by dt. When one rotation is completed, angle covered is 2 pi. Time taken for that is called as time period. So 2 pi by t, that's the formula for angular acceleration, angular velocity, you know it. From that I can write time period as 2 pi into root of y by a. That's the expression for the time period of a body in simple harmonic motion. Once you know time period, I can also write an equation for the frequency as reciprocal of the time period as 1 by 2 pi into root of a by y. So in this small derivation, in this small video, we have derived so many derivations for, say, equation for time period, frequency, acceleration, yeah, no, velocity, this equation and this equation. So this is a very important post in this chapter. And if you have not got it at a single time, I request you to go through this again. And if you still have anything, you can just post a comment there, right? Thank you for watching.